All right, let's look at this Unit 4 end of unit test review. So we'll just get started. So the first one, explain why log base 10 of 8,500 is more than 3 but less than 4. So our base here of 10, this when you look at the log base 10 of 8,500, it means 10 to what power is equal to 8,500. So I know 10 to the third is equal to 1,000, which is less than 8,500, and 10 to the fourth is equal to 10,000, which is more than 8,500. So it must be a number between 3 and 4, since 8,500 is between 1,000 and 10,000. Kind of the same idea over here. We have to fill in the blanks using whole numbers. So this time our base is 2. So 2 to what power is equal to 20? So the first thing I was thinking of was 2 to the third. I know is 8. That's less than 20. So if I multiply that by 2, we get 2 to the fourth, which is 16. That's still a little less than 20, so I need to do one more. 2 to the fifth would be 32. And so since 20 is between 16 and 32, the log base 2 of 20 would be between 4 and 5. So it takes a power more than 4 but less than 5 to reach 20. So this would be 4 and 5. All right, in the next section, like converting between exponential and logarithmic form. So the thing to remember is when you are starting with exponential form, whatever that base is also going to be the base of the log. So log base 2. And then the exponent is the answer. So it's log base 2 of 32 is equal to 5. And then going in the other direction, you should get like a math fact that like is true. So we have a base of 3 and the exponent is 4. So 3 to the fourth is equal to 81. And when you go backwards, you can always, it's like easy to check in your calculator. Let's see here. 3 to the fourth, see, it is 81. Okay. Here where the base of the log is not written, it's because it's a base of 10, which is, so it's assumed when there's not a base written that the base is 10. And so this is 100,000, it's equal to 10 to the fifth. So 10 to the fifth is equal to 100,000. And then the last one here, 5 squared is 25. So our base is 5. So log base 5. And then the exponent is 2. So log base 5 of 25 is equal to 2. All right, so that was the basics of just changing forms. Now we're going to put that into use here to solve some problems. So the first one, uranium-237 has a half-life of approximately 1 week. So we have a function here. We have a negative w in the function. Don't worry about that exponent. It's because it's a half-life, so it's decaying. And so our base 2, but then to a negative exponent would make it decay. So this function is already written for you. You just need to be able to work with it. So we'll do that. So it gives the amount of an 80-gram sample of uranium-237 remaining after W weeks. So, but like I said, the function is already written for us. Without using a calculator, write an expression to represent the number of weeks until there are 8 grams of uranium-237 remaining. So this is going to be our total here. We're looking for a total of 8. So it's going to start out with an equation, 80 times 2 to the negative w is equal to 8. And so this current equation hasn't been solved for the number of weeks. So in order to write an expression to represent the number of weeks, we have to actually solve this equation for w. We're just not going to put it into the calculator to get an answer. All right. So our first step, I'm going to do my steps in this blue color. So here's our equation. We have to isolate 2 to the negative w by dividing both sides of the equation by 80. So I get 2 to the negative w is equal to 8 divided by 80 is 1/10 or 0.1. And so I have the base and exponent all by itself. So now we need to just switch to log form. So our exponent, the negative w, the whole thing comes down. And it's equal to the log base 2 of 0.1. So this would be the answer if this was positive w, but it's negative w. And so we have to get rid of the negative over here. And when we divide both sides by -1, it literally makes the w positive and the log base 2 of 0.1 negative. And that's the answer. All right, let's look at the next page. We've got a couple more story problems. Next is about some mold on bread. An expired loaf of bread was found with mold on it. The mold is growing exponentially. Again, we're given the function. So this is great. You're not going to need to write functions. You just have to be able to use them and solve them. It's the amount of mold covering the bread in square centimeters after X days. All right. How much of the bread was covered when it was first found? So first found, that's the initial amount. That's our 2 right there. So it'd be 2 square centimeters. You could always plug in a 0 here for the exponent, but you would still get an answer of 2. So there's no reason to do that. What does the 0.088 represent in this context? So that is the continuous growth factor. Continuous growth factor. And we can say 0.088 or 8.8%. Okay, so as a decimal or as a percent. Next, write an expression for the number of days. Oh, we're using 8 again. In which 8 square centimeters of the bread will be covered in mold. Okay, so we're going to take our equation here. 2 times e to the 0.088x is equal to 8. This time, the base of the exponent is e, and so we're going to isolate the base and exponent by dividing both sides by the 2. So we get e to the 0.088x is equal to 4. 8 divided by 2 is 4. Next, we've got the base and exponent all by itself. So we're going to bring the exponent down and convert to log form. 0.088x is equal to, since the base is e, we'll use the natural log of 4. And then the last step would just be to divide by the 0.088 to get the x all by itself. So x is equal to the natural log of 4 divided by 0.088. And then D just says to use your calculator to evaluate the expression. So let's do that. So the natural log of 4, remember to close those parentheses before dividing by the 0.088. 15.75, so about 15.8. I think these are days. Yes, days. So I'm going to say X is about 15.8 days. All right, we've got another kind of story problem having to do with another function that's representing continuous growth. This time it's with money. So this equation models the balance of a savings account after X years. What was the initial investment? Again, you could plug in a 0 for X, but you would get $1,500. We know our initial amount is this value here. Okay, so $1,500. And what does the 0.05 mean? It means it's the continuous growth. In this example, it would be interest because it's a savings account by 0.05 or 5%. Okay, so now we're going to write an expression for the number of years it will take for the account to have a balance of $20,000. So we have 1,500 times e to the 0.05x equals 20,000. So that's the equation that we need to use. But if we want the expression to represent the number of years it will take for the account to have this balance, we actually have to solve this for x, because as is, that's just an equation. It needs to be solved for x to answer the question. So we're following, I hope you notice that we're following the same steps. This is like the third equation in a row that we've solved. And every time, oh, I didn't mean to switch back, but it's okay. Every time we're following the same steps. We're isolating the base and exponent, then switching to log form, and then solving from there. Okay, so when I put this in the calculator, I didn't get an ending decimal, so I'm just going to leave it as a fraction and deal with it later. So I have e to the 0.05x is equal to 20,000 over 1,500. And so bringing down the exponent and converting to log form. So 0.05x is equal to the natural log, again, our base is e, of 20,000 over 1,500. And then divide by the 0.05. So x is equal to the natural log of 20,000 over 1,500. And then that's divided by the 0.05. Okay? And then we just have to put that into the calculator. So the natural log of 20,000 divided by 1,500, close the parenthesis, and then divide by 0.05. 51.8, so I'm going to say about 52 years. It doesn't say how to round it, so I could make that choice myself. I have all the work back here to support it. So as long as all of that work is shown, then however you round is kind of irrelevant. It's up to you, unless it says. Okay, Home stretch. We've got actually three more problems, all having to do with graphs. I'm like the super itchy nose this morning. All right. So Bert is a beekeeper. He already has a bee colony that is doing quite well, but he wants to try a new type of bee box that is supposed to help the bee population increase more quickly. Bert is going to measure the difference between his established colony, which is colony A, and the new colony, colony B. Both graphs for both populations are shown in the diagram at the right. Okay. What are the approximate coordinates of the point of intersection of the two graphs? Okay. So here's the point of intersection. And let's see, it looks like this is counting by ones. So it looks like this is at 9. And then this one, it's counting by like 10,000. So let's see here, 10, 20, 30, 40, but not quite to 50. So maybe about like 48,000. So I'm going to say 48,000. But then what does it mean in terms of the two bee populations? So this axis is time, and this axis is the bee population. So I need to make sure that I include both of those words in my response. So I'm going to say after 9 weeks, both populations are about 48,000, meaning they are the same. Okay. All right, so the population of colony A, 30,000 times e to the 0.05x. When will this reach 100,000? Okay, so we want to take this equation and set it equal to 100,000. It says explain your reasoning by showing your work. That's how we do it, right? We set up an equation, we show the steps to solve it, and then we don't even really have to use any words or anything. It's so amazing. I love that about math. Okay, 30,000 times e to the 0.05x equals 100,000. Okay, so again, I think this is the fourth equation now that we're solving. Same steps. Here's our base and exponent. We're going to divide by this 30,000. I feel like I skipped some problems. Oh yeah, I did. I'll come back. I thought this was a quick video. All right. Maybe I'll make a separate video for 5 and 6. Yeah, I will. Okay. So here we go. So we're going to solve this by dividing. Now, again, when I put this in my calculator, I get, so 100,000 divided by 30,000. I get, ew, yuck. So I'm going to go math, enter, enter, and it's just 10/3. So I'm going to use the fraction 10/3 rather than a decimal. Okay, so e to the 0.05x is equal to 10/3. All right, so we're going to go ahead and switch to log form. So our exponent comes down, 0.05x is equal to the natural log of 10/3. Divide by the 0.05, so the natural log of 10/3 divided by 0.05. And then put that into the calculator. So the natural log of 10/3 close the parenthesis, and divide. 24.07, so about 24.1. Okay, it says time in weeks up here on the graph, so that's going to be weeks. So about 24.1, so I'm going to say 24.1 weeks. Excuse me. All right, so we've got two more problems that have to do with graphing. And so first we have y equals the log base 2 of x. So our base is 2. Remember, in a log graph, the y value is the exponent. So that's kind of a big deal that you understand. This is the exponent. And then the x value here is going to be like the answer. So this would be the same as 2 to the y is equal to x. Okay? So for this statement here, explain how you know the 0.42 is on the graph. Well, this would be our exponent, right? 4 is the x, 2 is the y. So 2 is the exponent, 2 to the second, because the base is 2 as well. So I know this is on the graph because 2 to the second is equal to 4. Oh no, my camera froze. There we go. 2 to the second is equal to 4. So that's how I know that this point is on the graph. What's the y-intercept? Well, if I just look at the graph, like it looks like it's at 0, right? But don't be fooled because it's just a really big scale. Like this goes to 200. So on our x, I think I said y-intercept, but I meant to say x-intercept. For an x-intercept, this is when y is equal to 0. So if I just put a 0 here for y, 2 to the 0 is equal to 1. So again, the answer is the x value, and the exponent is the y value. So that's the x-intercept. And then finally, will the graph meet the line y equals 10? So for the log base 2 of x is equal to 10, remember this is our base, this is the exponent. So 2 to the 10th is x, right? So x is equal to 2 to the 10th, base to the exponent. So 2 to the 10th is, let's see, 2 to the 10th is 1024. So the answer is yes when x equals 1024. All right, and then kind of similar questions here, but this time it's y equals the log base 5 of x. And remember, if we were to put this in exponential form, y is our exponent, so 5 to the y is equal to x. Okay, so how do you know the point 125.3 is on the graph? So 125 would be the x value, 3 is the y value. So if we put in a 3 here for y, we get 5 to the third, which is 125. So that's how I know. What is the x-intercept? Okay, so again, the x-intercept is when y is equal to 0. And so I'll put 5 to the 0. 5 to to the 0. 5 to the 0 is equal to 1. So this is our x, right? X is the answer, so 1. Y was the exponent, so 0. So the x-intercept is 1, 0. And then finally, will the graph meet the line y equals 5? So we have to set this up. The log base 5 of x equals 5. So base and exponent, that means x equals 5 to the 5th. So what is 5 to the 5th? 3,125. So the answer again is yes when x equals 3,125. All right. Okay, let's see here. I think I'm going to end this video and then make another one for the part that I skipped on accident. So thanks for watching.